Dear students, welcome to part 3 of module 5, Design of Machine Elements 2. Myself, Harikrishnan C, Assistant Professor, Mechanical Engineering Department, Rajagiri School of Engineering and Technology. In this lecture, we will be discussing the problems from V-belt drive and we will be discussing the fundamental theory and working and some problems from chain drive. Here we have problem 5.5. This problem is from K. Raghavendra textbook, page number 169, question number 20. Select a suitable V-belt to transmit 15 kilowatt to a compressor. The motor speed is 1200 rpm and compressor pulley runs at 400 rpm. Here power is given and the speed of motor driver NS is 1200 rpm and NL is given, it is 400 rpm. Here we have to design a suitable V-belt. Here we have the solution for this problem. We have power value NS and NL. From NS and NL we can find the velocity ratio I, and first step of this given problem is preliminary decision. Assume that the pulley is made of cast iron because of the damping property. Based on given power and combination of driving and driven members, the service factor for driven member, that means the compressor, is taken as Ks is equal to 1.2 from the column 5 of table 14.19, assuming light service and operation, continuous operation. And next we have the design power PD is equal to P into Ks equal to 15 into 1.2 equal to 18 kilowatt. And next you have to select which type of the belt. Referring to the table 14.14 of page 314 of data book, we have PD 18 lies in range of 10 to 70 kilowatt. Hence we have to select the type C belt having nominal top width 22 mm, nominal thickness 14 mm and maximum velocity Vmax equal to 25 meter per second. Next step, we have to find the pitch diameter of motor pulley, that means the driver, where D is equal to 630 cube root of PD by W max, where W max is equal to 2 pi n by 60. We will be getting a value of 125.66 radians per second, and D is equal to value is obtained as 329.66. Like the previous problems, we will have a standard value of pitch diameter C of the belt is 400 mm. You have to refer the previous problem to check how we can find the standard value. Then the pitch diameter of the driven pulley, capital D is equal to, we have the equation with an epsilon value. Here we can neglect epsilon value and D is equal to small d into I. Capital D is equal to 400 into 3 equal to 1200 mm. That also you have to standardize with the table. You will be obtaining the value as D is equal to 1250 mm. And here the revised velocity ratio I equal to capital D by small d, the fifth step, the standard size. Revised velocity ratio equal to I is equal to capital D by small d equal to 3.125. Sixth step, we have to find the belt speed V is equal to pi dn by 60. When substituting that values, we will be obtaining the velocity is equal to 25.13 meter per second. An approximate center distance that we discussed when we discussed about the fundamental theory of V-belt in the previous video. C approximate is equal to greater than or equal to 1.5 capital D plus small d. and approximate center distance will be obtained as 2475 mm. This equation is available in 14.2d of data book. And then we can find the pitch length of the belt. We have the equation very similar to the flat belt drive, and here we have factor of 1.57 in the second quantity, capital D plus small d. So equation is 14.15b. When you substitute that equation, you will be getting the value of L as 7613.5 mm. For C belt, the nearest standard nominal pitch length is L equal to 7625 mm and nominal inside length is equal to 7569 mm. The exact center distance equation that you can, the above values you can obtain from table 14.17, and then you can find the exact center distance where you can find the value of C using this equation, where A can be found from this equation and B can be found from this equation, where D, small d and L are the parameters that we obtained in the previous steps, and substitute these values, find A and B, and substitute in C, you will obtain the value of C as 2512.08 mm. Then find the value of angle of contact of driver pulley. Angle of contact of driver pulley equation is theta is equal to 14.1a. Substitute that value where d, small d, c, everything is known. Substitute that value, you will find the value of theta s. Then you can find the number of belts, where the equation used for finding the value of number of bell is available in 14.14, where n dash is equal to P into Ks divided by Kw, Kl, Ka, where P is the drive power in kilowatt, Ks is the correction factor according to the service, Kl is the correction factor for length, Ks is available in table 14.19, Kl is the correction factor for length, it is available in table 14.20, Ka is the correction factor for arc of contact, it is available in 14.21, Kw is the rating of the V belt, it is available in table 14.18. And then you can substitute, for substituting that values, we have to find DE, where DE is used for finding the kilowatt rating, this equation. Here you need DE. How to find DE? From where we will obtain this equation for kilowatt? Kilowatt equation is obtained in 14.13c. It is available in page number 295. You can find the value, find the equation from the page number 295, and you have to substitute the value for D here. For we have the equation for DE, KD into D. If you are substituting that value, I is equal to, we obtain the value for I and we have the value for D. When you are substituting that value, you will obtain the value for DE as 456 mm. But from table 14.18, the maximum value of DE is 300 mm for a C belt. So we can substitute the value 300. Here we will be adopting the value of DE as 300 mm. So everything is known in this equation for the kilowatt rating. So substitute that values and find the value for kilowatt rating. It is equal to 12 kilowatt. You will obtain this value as 12 kilowatt, and this is approximately, this is same as in the table 14.18 for V is equal to 25 meter per second and D is equal to 400 mm for C belt having nominal inside length of 7569 mm. Then the correction factor for length KL is equal to 1.16 you will obtain from table 14.20, and correction factor for arc of contact you will obtain from K is equal to table 14.21, you value obtained as K is equal to 0.95. Then substitute those values of PD, KL, KA and KW. You can find the value of the number of belts required. Then number of belts is obtained as 1.36. Then the value for number of belts is 2 belts. And here after this problem you have to mark the specification of belt. Here it is C7569 C belt, and in the first step we obtained the belt dimensions, and there was the nominal top width was 22 mm and nominal thickness was 14 mm. So substitute that values and draw a figure like this. Here we are moving to the next session, the chain drive. Chain drive is an intermediate between the belt and gear drives. It has some features of belt drives and some of the gear drives, and we will discuss the advantages of chain drives in the next slides. Here we will discuss what is chain and what is a sprocket and what are the applications. Here the chain drive consists of an endless chain wrapped around the sprockets as shown in this video or the animation, and the chain can be defined as a series of links connected by pin joints. The sprocket is a toothed wheel with a special profile for the teeth. What are the applications of chain drives for as the power transmission? For that means we are using for the power transmission or transmission from one shaft to another, and hoisting chains for long-lasting use for the lifting of loads. Then we are using the pulling chains, elevators and conveyors. What are the advantages of chain drives? Chain drives can be used for long as well as short distances. They are particularly suitable for medium center distance where gear drives will require additional idle gears. Thus, chain drives can be used over wide range of center distance. And here, a number of shafts can be driven in the same or opposite direction by means of chain from a single driving sprocket. Then chain drives have small overall dimensions than belt drives, resulting in compact unit. Here the chance of slip is very less. We can say that no slip condition, and the efficiency of the chain drive is high for properly lubricated chain. The efficiency of the chain drive is from 96 to 98%. And chain drives does not require initial tension, therefore the forces acting on the shafts are reduced, and the chains are easily replaceable. And what are the disadvantages? Here, chain drives operate without full lubricant film between the joints, unlike gears. This results in more wear at the joints. The wear increases the pitch of the chain. The chain is stretched out and may leave the sprocket if the tension is not adjusted from time to time. It is not suitable for non-parallel shafts. Actually, bevel and worm gears and quarter turn belt drives can be used for non-parallel shafts. And here some effect is there. It's called polygonal effect. We will discuss in the coming slides. Chain drive is unsuitable where the precise motion is required due to a polygonal effect. The velocity of the chain is not constant, resulting in non-uniform speed of the driven shaft. Then it requires a housing due to safety, and as well as we need a constant environment. If you are applying some lubricant, some dust particle may adhere to that may decrease the efficiency. So we need a housing. Then compared to the belt drives, chain drives require precise alignment of shafts. However, the center distance is not critical as in the case of gear drive. Then we need proper maintenance and lubrication, and the chain drives generate noise. There are different types of chains with respect to their purpose. Chains are classified onto different mainly to three main groups. They are load lifting chains, also called the link chains, and howling chains, and one more is there, it is power transmission chains. Actually, the load lifting chains are used for uh, suspending or raising or lowering loads in material handling equipment. The popular example of this category is a link chain. Here it is illustrated in figure, and it has good flexibility, operate with small diameter pulley and simple design and less noise. And the cons are heavy in weight, jerks and overloads, failure in sudden and total, operates lower load. These are the disadvantages of these chains. And next one is hauling chains. Hauling chains are used for carrying materials continuously by sliding, pulling or carrying in conveyors. The popular example of this category is a block chain, and it is illustrated in figure. Here it is illustrated. It is consist of slack plates of simple shapes and pins. It operates at medium velocities of up to 2 to 4 meters per second. So one more category is there, which is the power transmission chains, which are used for transmitting power from one shaft to another. It is in our chapter we will be following and we will be studying more about the power transmission chains. So we will be discussing about power transmission chains in the next upcoming slides. See, the power transmission chains, the major parts of power transmission chains are pin, roller, bush and inner plate, outer plate. Here the pin is given here, this is the pin, and the roller is given here, this is the roller, and we have the bush, this is the bush, and the inner plate, outer plate. This is the parts. Pin which passes centrally through this bush, and roller surrounds the bush and turns freely on the bush. Bush surrounds the pin and turns freely on the pin, and inner plate connect two bushes. Outer plate connect two central pins by interlinking two inner plates. Here in this slide, we are going to explain how ISO chain number is specified. Here we have some numbers are specified here, 08B and 16A. The chain number is given like 08B or 16A is consist of two parts. The number followed by a letter. And the number in 2 digits express the pitch in 16th of an inch. The letter A means American Standard ANSI series, ANSI series, and the letter B means British Standard series. Most of chain manufacturers are American, and their ANSI series is popular in engineering industries. Let us consider the designation 08B. The pitch of this chain is 8 by 16th inch or 8 by 16th into 25.4 mm. That means 12.7 mm. The letter B indicates British Standard Series. Let us consider the case of 16.16a. The pitch of this chain is 16 divided by 16 inch or 1 inch. That means 25.4 mm. The letter A indicates American Standard or ANSI series. Here we are going to explain the braking load. Braking load is defined as the maximum tensile load which, if applied, will result in chain failure. So braking load is also important in the case of the chain design. And here we have a simple chain as well as duplex chain. Simple chain we can it is self-explanatory from the figure of as also the duplex chain. And symbols, when we are representing a symbols chain, we will be adding one -1 to the suffix, and here for the duplex chain we will be adding 2. The engagement of chain on a sprocket wheel is shown in this figure, where the D is the pitch circle diameter of the sprocket and alpha is called the pitch angle. The pitch angle diameter of the sprocket is defined as the diameter of an imaginary circle that passes through the centers of pins as the chain is wrapped on a sprocket. Here you can find these relations. Alpha is equal to 360 by Z, where Z is the number of teeth on the sprocket, and you can obtain D is equal to P by sine alpha sine 180 by Z. This you can obtain by this relation, where sine alpha by 2 is equal to P by 2 by D by 2, or capital D is equal to P by sine alpha by 2. In that equation you can substitute this equation, you will obtain finally this equation. You can refer page number 548 of our Bhandari textbook, the textbook by V.B. Bhandari, Design of Machine Elements. Then this is the equation for average velocity of the chain. V is equal to pi dn by 16 raised to 3. This you can replace by pi d by z into p, where p is the pitch and z is the number of teeth. Then the length of the chain that you can find by L is equal to Ln into P, where L is the length of the chain, Ln is the number of the links in the chain, and P is the pitch. This is P. Here we will be discussing about polygonal effect. The chain passes around the sprocket as a series of chordal links. This action is similar to that of a non-slipping belt wrapped around a rotating polygon. The chordal action is illustrated here in these two figures, where the sprocket has only 4 teeth. It is assumed that the sprocket is rotating at a constant speed of n rpm. Here in this first figure, the chain link AB is at a distance of d by 2 from the center of sprocket wheel, and its linear velocity is given by Vmax is equal to pi dn by 60 into 10 raised to 3. And in this B, in case B, the link is at a distance of d by 2 into cos alpha by 2, this distance from the center of the sprocket, and its linear velocity is given by this equation. V minimum is equal to pi dn cos alpha by 2 divided by 60 into 10 raised to 3. It is evident that the linear speed of the chain is not uniform but varies from Vmax to V minimum during every cycle of tooth engagement. This results in a pulsating and jerky motion. The variation in velocity is given by this equation. As the number of Z increases to infinity, cos 180 by Z or cos 180 by infinity, that means cos 0, will approach unity, and Vmax minus V minimum will become 0. Therefore, the variation will be 0. In order to reduce the variation in chain speed, number of teeth on sprocket should be increased. The power transmitted by the roller chain can be expressed by this elementary equation, P is equal to Fp by 1000, where F is the allowable tension in the chain in Newton, V is the average velocity of chain in meter per second. However, it is not easy to determine the allowable tension in the chain. It depends on number of factors such as the type of chain, pitch of the chain link, number of teeth on the smaller sprocket, chain velocity, the type of power source, and driven machinery and system of lubrication. Actually, in practice, the rating of the roller chain is obtained on the basis of 4 failure criteria. One is the wear, and the next is the fatigue, and next one is the impact, and third one is the galling. I will explain the galling. All the others are very, very familiar names. Galling is the stick slip phenomenon between the pin and the bushing. When the chain tension is high, wells are formed at the high spots of contacting area. Such microscopic wells are immediately broken due to relative motion of contacting surface and leads to excessive wear even in presence of the lubricant. Here the design procedure for the chain drives. First we will find the velocity ratio as I is equal to N1 by N2 and Z2 is equal to the Z2 by Z1. And next we will find the Z. Based on the velocity ratio, select the number of teeth on the smaller sprocket Z1 using the table 14.36a and obtain the Z2 is equal to I into Z1. Z1 should always be an odd number. And next we will calculate the pitch as equation P less than or equal to 10 6 into 60.678 by N1 the whole raised to 2 by 3. This is available in our data book, equation number 14.22 to 2b. Then here the N1 is the speed of smaller sprocket in radians per second, and we have to standardize the pitch to the nearest value by the standardizing table 13.14.39a and 14.39b. Then find the chain number, measuring a load and the braking or ultimate load. Then the next step is the calculation of the PCD of sprocket. Equation D is equal to P by sine 180 by Z, and we can find the value of P from this step. This step we can find the value of P and substitute this value for finding the PCD, and this equation is available in 14.22. Then find the velocity of chain. It is the PZN by 1000, equation 14.22a. Then find the calculate the tangential force. F is equal to 1000 P by V, and this equation is available in our data book. Then calculate the working load per strand FW. FW is equal to FU by Fs into Ks, where you will find the FU from you can find the value of FU from the third step, where you've obtained using this table. You can find, I told you, braking or ultimate load FU you can obtain from this step. And the Ks is the service factor that is available in the table 14.35. Then the factor of safety, table 14.37, that you can find. Then the next step is to calculate the number of strands. The equation is J is equal to F by Fw. It is equation 14.22H. Next we have to find the factor of safety, actual factor of safety. For finding actual factor of safety, there is an equation 14.22. There Fu is there, F divided by Fu by F plus Fc plus Fs, and the Fc you can find by W dash V square by G. In that W dash you will obtain from the third step, and the next value Fs is equal to K2 into W dash into C1, and K2 is the coefficient of sag and C1 is the central distance. Here the center distance can be obtained from this equation. Then you can find the length of pitch. Calculate the chain length in pitch as LP. You will be obtaining this value. You can substitute CP as this and alpha value as this, and then find the chain length L is equal to P LP. From the obtained value of LP, then determine the exact center distance by replacing CP with CE by P in the this step. Then you will get the value of exact center distance CE. Here we have the first question from roller chain. This question is from our Raghavendra textbook K. Raghavendra, Design of Machine Elements. Here in this problem, they are asking to design a roller chain for a bucket elevator to be driven by a gear motor. The gear motor has 6 kilowatt and runs at 120 rpm. The speed of the bucket elevator is 60 rpm. The center distance is 1100 mm. The elevator operates 10 hours per day with mild shock. Then we have to design a roller chain for this application. Then first of all we have to identify the given data. Here we have the values. Power is given 6 kilowatt. Then the speed N1 is given 120 rpm, N2 is 60 rpm. Then the given center distance is given, C1 is equal to 1100 mm. Then it is some service condition is given. The service condition is mild shock working for 10 hours per day. Then similar to the previous step, here we have the power is given and the N1 value, N2 value, C1 value is also given. Then the service condition is given that mild shock working for 10 hours per day. First you can find the value of I using N1 by N2, the simple equation 14.36. You'll get the value of velocity ratio as 2. Then referring a number of teeth, referring to the table 14.36, there is a ratio of I value. The range is 1 to 2 and the value of the number of teeth in smaller sprocket range is 30 to 27. For our design we will be selecting the number of teeth in the smallest sprocket as Z1 is equal to 27, Z2 is equal to I into Z2, Z1, so it is equal to 27 into 2 equal to 54. Then find the value of pitch using this equation, where in this equation 14.22b, value of N1 is given in rotation per revolution per second. Substitute the value of N1 in revolution per second and find the value of pitch. Using this pitch value and from the table 14.39 we have a lot of information. 14.39 corresponding the value of the nearest standard pitch P is 88.90. So for the 88.90 we will be adopting the chain number 228B in the page number 341 and table number 14.39B. And the measuring load is obtained as this and breaking or ultimate load is obtained as this. So we will be selecting the chain as 228B. Then find the PCD, the pitch circle diameter of the sprocket, using the simple equation P by sine 180 by Z, where P value is obtained as 88.90 and divided by sine 180 by 27. And for the largest sprocket, D2 is equal to P by sine 180 by Z. It is also, you can substitute and find the value for the D1 and G2. Then the velocity of chain that you can obtain by using equation 14.22 and the simple equation P set that we discussed in the previous slide, that you can substitute and find the value for velocity of the chain. Then find the tangential force acting. It is F is equal to 1000 P by V. That also you can substitute the velocity obtained here, and then you can find the value for tangential force. Then the allowable working load per strand is Fw is equal to Fu by factor of safety into Ks, where Fu is 129.06 obtained here, and service factor Ks for nearest shocks up to 10 hours per day, that we will obtain from a table. The factor of safety is from the table we can have for 50 you will be getting the factor of safety of 70, and for 200 we will be getting a factor of safety of 8.55. For based on this, for N1 is equal to 120 rpm, do some interpolation and find the factor of safety. Find factor of safety as 7.72. You will be getting the value of factor of safety as 7.72. Here you have the allowable working load per stand Fw. Substitute the previous three values. Here you will be obtaining that value as 8798.7 Newton. Then find number of strands using 14.22H by these equations. You will be getting the value of 0.142. approximate it as one strand, then find the actual factor of safety. We have obtained the factor of safety from the tables as 7.72. Here you will be getting a value by this equation, and we will compare the value between actual and the value from the tables. So here the actual value is j into fu by f plus fc plus fs. Here fc you can substitute by this equation and fs you can substitute by this equation. In this equation, k2 value that you can obtain the coefficient of for sag from the table 14.38 and substitute that value, and you can find the fs, the actual factor of safety, as 8.78, and comparing with the factor of safety from table 7.72. Here the factor of safety actually is greater than the factor of safety from obtained from the tables, and the selected chain is safe. Then find the chain length using this 14.22 equation. LP is equal to 2CP cos alpha plus half Z1 plus Z2 plus alpha into Z2 minus Z1 by 180. This is very similar to the belt drive equation. For that CP value and alpha value you have to calculate. CP value is C by P, and the alpha value is sin inverse D2 minus D1 by 2C. All parameters are known, so substitute those values and find alpha and CP. Then substitute this CP and alpha value here, find the length of chain in terms of pitch. You will be getting 66 pitches, and then substitute find the value of length of the chain length by using this equation. L is equal to P into LP, and the next procedure is to find the exact center distance. You can find the exact center distance by replacing CP with CE by P in the LP equation, this equation. There you can find the value for CE, and that CE is obtained CE is equal to this value. So CE, from this calculation, CE you can obtain as C is equal to 10.64.23 mm. This is the exact center distance. The silent or inverted tooth chain is represented here. Each plate has two teeth with a space between them to accommodate the mating teeth of the sprocket. The sprocket teeth have trapezoidal profile depending upon the type of joint between links. The silent chains are divided into two groups, Reynolds chain and Morse chain. In the Reynolds chain, the links are connected by pins, resulting in sliding friction. In rocker joints, actually the rocker joints are used in Morse chain. Compared with the roller chains, silent chains can be used for high speed applications. They operate more smoothly and less maximum quietness can be obtained, and these are more heavier and more difficult to manufacture and more expensive comparing to the roller chains. Their applications are limited due to these reasons. Now we are concluding the module 5, and I request all of the students to refer V.B. Bhandari textbook and K. Raghavendra textbook for doing problems and theory. All of you practice the problems well. We will meet again with module 6. Thank you.